It might have been the private one.
All right.
I see, I see.
Right.
Yeah.
Ready to start? All right. So it's my pleasure to introduce John. John was an Air Force pilot. Well, he's still an Air Force pilot. But then he decided to do something more exciting. So he decided to apply for a PhD. And after some competition with MIT, finally, I convinced him to come to Stanford. And for the past 3 years, he's been working in my lab on the topic of control of infinite dimensional systems. That is, systems that are described by partial differential equations. So those are systems that, for example, arise in soft robotics, or when you want to control a system that is interacting with fluids. And he has a lot of exciting results that he talked about. I could tell many, many stories about John. I think that he offered me to be the first passenger after he gets requalified for
Yeah.
jet flight that will happen in February, right?
I look forward to
So
this.
I trust him so much.
I really look forward to
Yeah,
this.
he's challenging me that makes me pay for everything I've done to him. But anyway, without further ado, look forward to your talk.
Thanks, Mark. I really appreciate the introduction. So good afternoon, everyone. Thank you for being here today. As Marco said, my name is John Alora, and I'm excited to share the culmination of really 4 years of research with you. Over these years, I've been exploring the challenges and opportunities in continuum robot control, an area that really intersects robotics, applied math, and control theory. My thing will start. Okay. Okay, so before diving into my specific research, let me try to set the stage by looking at where we are in robotics today. Robotics is advancing rapidly from household robots that can handle complex daily tasks to drones that can outperform human champions in drone racing. And I think what's critical here is that these achievements have relied on having accurate models, whether that be used for direct control or simulation-based learning. But what if there are systems where deriving a model useful for control is difficult? And this is the case for continuum robots, an emerging class of autonomous systems. Unlike traditional rigid body robots, continuum robots exhibit a dynamically evolving structure that's inspired by nature. And these systems can bend, stretch, and flex like living organisms, allowing them to navigate complex and constrained environments with remarkable dexterity. But with great flexibility comes great challenges. Continuum systems are inherently multi-physics, combining mechanics, material deformation, and in some cases, fluid interactions. And they operate across multiple timescales. They also have many more degrees of freedom compared to control mechanisms, making them severely underactuated. And so this presents a variety of technical challenges. Namely, these phenomenon result in complex models which need to describe how they deform and move, as well as the intricate motions between or interactions between multiple physical phenomena. Second, these systems are often operate with unknown boundary conditions. For instance, in practical applications like soft robotic surgery or underwater exploration, external forces and constraints may not be fully observable or predictable, adding uncertainty to the modeling process. And lastly, practical deployment for precise control tasks can result in models that are thousands to millions in dimension. So these complexities really make deriving models for control incredibly difficult. More precisely, let's sort of consider this constrained optimal control problem on the left, where we're trying to find a sequence of control while minimizing some costs on performance variables and input, subject to the physics of the system. Now, due to the complex physics at play, inaccuracies that stem from the first two challenges can result in models that deviate significantly from the true system, resulting in poor predictions and hence poor control performance. While the third challenge results in high dimensionality of the model, making solving this optimal control problem intractable, especially if we want to do this in real time. And there are various approaches to try to overcome these challenges, which we can essentially group into two classes: data-driven approaches and equation-based methods. Data-driven approaches try to learn dynamics from observed input-output transitions. Examples of these types of models could be neural networks, Gaussian processes, operator theoretic methods like dynamic mode decomposition. And the inherent advantages of these approaches is that they're equation-free and non-intrusive. So you only need the data to characterize this model. The issue is that they're prone to overfit, and it's difficult to quantify the uncertainty of the model, which presents challenges for safe deployment. On the other hand, we have equation-based methods, which may also use data, but they use it to compress an already existing high-dimensional model, for example, like a finite element model. Now, these include methods like projection-based model reduction, where you're trying to understand the evolution of your system's behavior on a linear subspace. And the high-fidelity model here serves as a really strong regularizer that prevents overfitting. But that same property that makes these methods cumbersome to implement, because extracting models from computational solvers is an encumbering and code-intrusive process. Furthermore, these models may still be too high-dimensional for actual real-time control when we use these models in an embedded setting. And so in this work, I attempt to get the best of both worlds by learning models from input-output data, but focusing on the causal dynamics in between. And to that end, I'll tailor the learning scheme to target low-dimensional structures within the Continuum robot's phase space. These are called spectral submanifolds. And the goal here is to really leverage these structures to learn low-dimensional models for safe and data-driven control. And so in this talk, I'll focus on three core contributions I've made throughout my PhD, namely the introduction of a model-based control methodology that leverages sort of learned dynamics on these spectral submanifolds, a method that guarantees that this control scheme is robust to model error, and an extension of this methodology to achieve even greater accuracy when the robot significantly deforms, bringing us one step closer towards controlling these robots at the limits of their design. This talk really summarizes the body of work I've published and presented to the broader robotics and controls community, all of which attempt to address the technical challenges inherent in enabling continuum robot autonomy. Now, I want to sort of ground these results by showcasing two types of robots. The diamond robot on your left is constructed from silicone and represented in both finite element simulation, that's approximately 10,000 dimensions, and an actual hardware replica of that robot. The control mechanism for this system consists of 4 cables pulling on its elbows to achieve a desired motion. The second robot we'll consider is this trunk robot, which is also made of silicone, represented by a roughly 4,300 dimensional finite element simulation. It's controlled using a system of 4 cables that terminate at the midpoint and another 4 that terminate at the tip. And the task is to have these robots, or to control these robots so that they follow a pre-designated trajectory. Okay, so now that you've seen the robots that we'll be working with, let me walk you through the framework that enables their control. In this part of the talk, I'll briefly introduce what a spectral submanifold is, how to find low-dimensional dynamics on it, and then describe our model-based control methodology. I'll then present results where I compare the spectral submanifold reduction-based method to state-of-the-art baselines. Okay, so throughout this talk, I'll reuse some terminology that may not be standard. And so to make sure we're all on the same page, I'll just briefly recall some basic linear algebra facts that hopefully will help us build some intuition, but being just precise enough to really appreciate the methodology. So we'll start with the dynamics of a stable linear system defined by x dot equals ax. In this system, there's different components of the dynamics evolve at different rates. And these are determined by the components as eigenvalues. The slow modes are the components that evolve the slowest and persist over time, while the fast modes are the components that fade quickly, okay? Now, by grouping these slow modes, we define what we call a spectral subspace, which is essentially the space that carries the sort of dominant long-term behavior of x dot equals ax. More precisely, this space is spanned, by the eigenvectors corresponding to the slowest eigenvalues. And crucially, this allows us to understand x dot equals ax in terms of the slow modes while ignoring the ones that don't contribute to its long-term behavior. And this is really the idea. This idea is really the basis for reduced order modeling, where we're trying to construct computationally efficient models, yet accurately capture the system's behavior by constructing models that focus on the slow, persistent behaviors of the system. Now that was for an unforced linear system. Let's ramp up the complexity a bit by adding, this nonlinearity, but still staying in this uncontrolled case. It turns out that under, technical non-degenerate conditions on the slow modes of the system, the flat plane, which defines the spectral submanifold or the spectral subspace, deforms into surfaces, nonlinear surfaces or submanifolds, which carry the dominant modes of the system. And so intuitively, I can obtain the linear part of the dynamics of my robot, say by linearizing at its resting position, and then grouping the slow modes commensurate with that linear part to define a spectral subspace. I then deform that flat plane into a nonlinear surface. And in the same way, the dominant dynamics of a linear system can be understood by this flat plane. We can understand the evolution of the dominant dynamics of a nonlinear system by this surface or submanifold. Now, an uncontrolled spectral submanifold is then defined as the smoothest of these surfaces. In other words, the surface that we can take the most derivatives on. And since this manifold is just a deformation of the spectral subspace, it has the same dimension, which means it's also low dimensional. Furthermore, it's an invariant surface, which means that once the trajectories land on this SSM, it stays on the SSM. And combining that with the fact that these robots' trajectories converge to the manifold exponentially fast, it is precisely the structure that effectively describes the dominant dynamics of this uncontrolled nonlinear system. Now, the nice thing in practice is that these SSMs actually exist for many dynamical systems, including our continuum robots. And when we add control, it turns out that these structures continue to exist, but in a time-varying analog of this unforced SSM. Now, recent work proves that the uncontrolled SSM actually survives as a time-varying manifold defined along the controlled trajectory, which too exists for our continuum robots. And intuitively, the new target trajectory is shown here actually takes over the role of a fixed point. And so the SSM, we can define an SSM that's attached along this controlled trajectory. And it's also exponentially attracting all of the trajectories of the robot onto it. And so when I talk about the dominant dynamics of my controlled robot, I'm actually talking about the dynamics on this non-autonomous SSM. Well, it turns out approximating the dynamics on the non-autonomous SSM is actually challenging and may not be necessary if the target trajectory is sufficiently close to the robot's resting equilibrium. And so in the first part of this thesis, what I'll do is rather than approximate the full time-varying SSM, which might be computationally difficult, we'll actually just approximate the uncontrolled part and then calibrate the learned dynamics for control. So we'll jump right into it. The desiderata of our model that we're trying to learn will be trying to learn a chart map, or in machine learning parlance, an encoder map, which encodes our observable measurements into reduced and latent coordinates. The dimensional dynamics in this reduced latent space, and a parametrization map or decoder, which decodes the reduced coordinates into our original observables. Now, tying it back to the sort of physical interpretation of the system, this chart map will be in the reduced coordinates defined by the dominant modes of the system, right? So we'll get these dominant modes via SVD or singular value decomposition of the system's evolution. We'll then obtain the parametrization map by fitting a function that minimizes reconstruction loss between the reduced coordinates and the observables, and then essentially fit control dynamics in our reduced space. Okay, great. But you're probably thinking, how is there any hope that you're actually learning the dynamics given some generic measurements? Well, luckily, we can rely on fundamental results in nonlinear dynamics, which basically say that there is hope in detecting these dynamics from data as long as you have enough measurements. And if you don't have enough sensors to measure, you can actually just take time-delayed measurements, and you can guarantee that you can detect these dynamics. So that's what we'll do. We'll pick sufficiently time-delayed measurements of the robot's end effector as the observables that we work with. Now, to infer the uncontrolled SSM, we'll start by collecting decaying trajectories of the system, observing, say, again, the tip of the robot. And to ensure our trajectories trace out the geometry of the surface, what we'll do is we'll truncate the transients from the trajectories to form our decaying data set. Once we've collected data that'll characterize the uncontrolled dynamics, we'll then collect controlled data by simply applying random inputs and measuring the system's response. And I want to pause here and sort of foot stomp a really important point, which is that we're deliberately disambiguating the uncontrolled and controlled trajectories because it allows us to better capture these dominant dynamics. Remember, our goal is not to fit a model to individual trajectories, but to this phase-space structure, to this SSM. And so fitting dynamics to the uncontrolled SSM serves as a really strong inductive bias towards fitting a model for control because control trajectories will be close to this surface. Now, with this curated data set, we can proceed to learn our appropriate maps. First, we'll infer the chart map by conducting a SVD on our decaying data set. And then, by standard principal component analysis, we'll just keep our, the top n singular values, capturing 99% of the variance in the data. This gives us, the left singular vectors of the data matrix whose leading n columns would then span this spectral subspace. And when we construct the SSM, the chart map can be sort of interpreted as defining an orthogonal projection onto the most persisting modes given by the spectral subspace. And now that we have the chart map, we can then take our trajectories and encode them into reduced coordinates, and then essentially fit a map which minimizes the reconstruction error between the reduced coordinates and the observable space. And since the SSM is smooth, what we'll do is we'll opt to regress over polynomial functions. But in principle, this can be any ansatz you'd like: radial basis functions, Gaussian processes, even neural networks. Knock yourself out. Similarly, we'll fit the uncontrolled reduced dynamics by minimizing one-step prediction error. But this will only give us a description of how the robot decays to its resting position from some arbitrary initial condition. And so to calibrate this model for control, what we'll do is we'll take our controlled trajectory data set and encode them into reduced coordinates using our chart map, and then essentially regress the difference between the flow that is predicted by the uncontrolled dynamics that we just learned and the flow of the true system that is encoded in the reduced coordinates, to then learn a control vector field which results in the controlled dynamics to the right. Now that we have all of the components of the model, the chart map, the controlled reduced dynamics, and the parametrization map, which reconstructs our measurements, let's see how its predictive capability fares. And to evaluate this, what we'll do is we'll collect a trajectory from the true robot by applying a random input sequence to explore its workspace. And then now that we have this data set, we'll randomly sample points along the trajectory. And for each of these points, ask our model to predict, the next n time steps. And now that we have sort of the model predictions and the true trajectory in hand, we can characterize the accuracy of the model, as shown here. Now, what we do here is we first evaluate the predictions of our data-driven and equation-based baselines, where here I'm plotting the 10 best and 10 worst predictions of each model on this trajectory. The way to sort of interpret this is that the more purple you see, the less overlap between the true and predicted trajectories, which denotes less accuracy. And what we see here is that actually, and this is for the baselines, we see that the equation-based but data-enriched models actually outperform the purely data-driven ones, which is unsurprising since the equation-based models, again, provide this strong inductive bias that allows it to generalize across different control tasks and overfit less than the purely data-driven methods. But then when we compare with our methods, we see that we're actually outperforming the baselines by a significant margin. This is evidence that we indeed can get the best of both worlds, namely that we can be equation-free and still learn structurally robust models. What I'm showing here is a model that learns the dynamics on the nonlinear surface, denoted SSMR, and a simplified version which learns a model on the flat plane called spectral subspace reduction, SSSR. And as expected, when we compare the two, we see that SSMR actually outperforms SSSR because these linear models are unable to capture the geometric nonlinearities that manifest as the robot traverses this trajectory. And here, what I'm doing is I'm just giving a more global perspective on performance, where we're doing the same exact evaluation as in the previous slides, but just for more points. We see that our nonlinear model outperforms our linear simplification again, and significantly outperforms the state-of-the-art baselines in continuum robot control. We see that despite the fact that our SSSR models are linear, they outperform data-driven baselines, showing that capturing the dominant dynamics with a well-structured model can actually be more effective than approximating nonlinearities indiscriminately. Furthermore, even though SSMR is fully data-driven, it outperforms this trajectory piecewise linearization method, which was derived and was a compression of the true finite element model, which is further evidence that we can indeed get the best of both worlds. And so now we close the loop and evaluate how well our model performs in trajectory tracking tasks. Specifically, what we'll do is that at each control period, we observe the state of the robot, encode its state in the reduced coordinates, and then solve an optimal control problem using our model to find the optimal actions. And the optimal control problem involves trying to achieve an objective while minimizing costs, subject to state estimate in the reduced space, the dynamics in that reduced space, and the desired observable and or performance variables, for example, the end effector of the robot, and the constraints on the robot. Now, remember that the original robot is thousands of dimensions. In this case, this robot was 10,000 dimensions. And the reason why we can solve this is because we use a lower dimensional surrogate to predict the robot's behavior. Surprisingly, though, when we compare SSMR-based models with our baselines, we achieve several factors of compression on top. This truly, I believe, allows for real-time control. Now, in light of our open loop results, unsurprisingly, we find that the SSMR and SSSR-based methods outperform our baselines. In this slide, I show the diamond robot's end effector tracking a figure 8 in the XY plane. We see that this trajectory is fairly slow and that most methods are able to proficiently track it. Nevertheless, our models still outperform the baselines in terms of relative tracking error. Now, the moment that we ramp up the speed a bit, we see that the same robustness story emerges. right? The purely data-driven approaches break apart, and the models, which are based on structural priors, remain robust. Furthermore, among these models, ours perform the best. Now, this observation highlights three things. Purely data-driven methods that just fit to individual trajectories tend to overfit, especially in the low data regimes. Priors essentially allow us to achieve better control generalizability. And we can actually get the best of both worlds, an equation-free method with the robustness capability of an equation-based method by focusing on learning the causal dynamics between input and output data. Now, similarly, for the trunk robot, we see that the SSMR-based methods outperform our baselines by up to a factor of 12 on diverse trajectories, including more challenging and arbitrary ones, such as this task where the robot is asked to follow this ASL logo. And encouraged by these results, we employed these models on a real-world diamond robot and observed similar performance gaps between the baselines and our SSMR-based models. So that wraps up the first part of this talk. In summary, what we did was we proposed an approach to approximate the dominant dynamics near an autonomous SSM. In doing so, we were able to learn compact representations of the robot in an equation-free manner, while outperforming both data-driven and equation-based baselines. And the reason why is because, again, we're learning the dynamical structure between input and output data. Now, up until this point, while we can sort of impose safety constraints in our optimal control problem, it's with respect to our model. And because this model is a compressed representation of the true system, the true system under control may not actually satisfy the safety constraints. And so in the second part of my talk, I'll tell you how we address this lack of safety guarantees by reasoning about the dimensionality reduction error and using it to design a robust model predictive controller. So let's recall that we're learning a model that's, again, anchored to this uncontrolled SSM and then calibrating that model for control. While this manifold or the surface is invariant for uncontrolled trajectories, it's not invariant for controlled trajectories. But what we can do is we can actually think of control and disturbance as forces that push the true system behavior off of the manifold. And what we'll do is we'll use that intuition to design a control scheme that controls the robot and ensures constraint satisfaction, even under model reduction errors. So in an attempt to build up that intuition, we want a controller that is uncertainty aware such that when it gets close to the constraint, rather than allow the true system to violate this constraint, it proactively reacts to prevent the system from violating the constraint or becoming unsafe. Now, the core of being able to do this is to first equip our model with an uncertainty estimate that tells it the worst case error at any given time. And then based on this worst case error, tighten the constraints for our model so that the true system is guaranteed to satisfy constraints and remain safe. Okay, so more specifically, suppose we have some constraints on our performance variables given by this inequality set. We tighten these constraints by constructing an error-bounding system which quantifies the uncertainty between the true system and the model, and then adding it to the constraint shown here. Now, to minimize conservativeness, what we'll do is we'll construct this error-bounding system so that it predicts error over the planning horizon. And so it can adapt its uncertainty based on its state and its control. Now, since we don't know the actual, the true system, which, by the way, is extremely high dimensional, this task of quantifying the uncertainty is highly non-trivial. Now, fortunately, the structure we obtained by learning models near uncontrolled SSMs will be useful in solving this problem. Here, we'll use that same intuition, as I said before, that control and disturbance push the true behavior of the uncontrolled manifold, the true system behavior off of the manifold, to help us characterize the uncertainty of our manifold-based model. Now, to be precise, I'll introduce some more notation, their corresponding or notions and corresponding notation. The charted system represents the true system evolution in the reduced coordinates, while the manifold restriction represents its evolution on the manifold. In addition, we have our SSMR model discussed in part 1, which gives a reduced prediction and commensurate prediction, and its commensurate prediction on the manifold, as shown here, which will denote as such. And the key idea is that by upper bounding the error between the true system and its projection to the manifold, as well as upper bounding the error between the prediction of our model and the evolution of the system in these reduced coordinates, we can actually construct an uncertainty estimate which upper bounds the worst case possible error between our model prediction on the manifold and the true system. And in doing so, looking at, sort of the first part, we can construct an error bounding system of the off manifold error. So when we stare at these equations, we see that it sort of aligns with our intuition, right? So I'll just be quick here. The laser's not working. We see that it can be sort of interpreted as being pushed off of the the system being pushed off of the manifold when it doesn't take into account control. We have essentially a control term which quantifies how much the control pushes the true system, shown here, off of the manifold, with the error being directly correlated with the magnitude of that control. We also have a term on the left side here, or on the left side, where which quantifies the rate at which trajectories are attracted to the manifold. So the larger the tendency these trajectories to converge to the manifold, the more accurate our model is. Now, for the second component, the reduced prediction error, we have a similar intuition. The first term, again, quantifies how fast the slow dynamics converge along the origin. The faster the convergence or the more negative lambda is, the faster it reconciles the prediction error. The second term accounts for how being pushed off of the manifold actually affects the model predictions. And so we'll use using these two quantities, we can then construct our uncertainty bound as being proportional to the reduced prediction and the off manifold error. And when we add this to the constraint and set as a tightening term, allows us to design an MPC scheme which guarantees recursive feasibility and constraint satisfaction, as well as asymptotic stability to a controlled set point. Now, to showcase the efficacy of our robust MPC framework, we consider the following example where we have a diamond robot's tip following a periodic square trajectory while staying within the desired workspace. And then after following this trajectory, try to track a set point on the boundary as close as possible. And to contextualize our method, we conduct simulation where we don't account for this model error. So this is just the nominal MPC framework, and where we manually tighten the constraints. And as expected, nominal MPC violates the constraints, while our ad hoc constraint tightening scheme requires hand tuning to the particular control task, which in turn could lead to conservative behavior, and perhaps during the trial and error of tuning may cause the system to actually violate constraints, which would not be safe. On the other hand, our method achieves zero-shot constraint satisfaction. The constraints dynamically tighten, and it's recursively feasible and correct. And so if we combine this robust MPC design with our model in part 1, we endow these robots the ability to safely act in the face of model uncertainty. Our methodology allows these robots to do this dynamically for any control task with minimum human intervention. Now, so far, all of the control tasks considered have been tracking trajectories in the planar direction. But if we want these robots to be more useful and perform closer to the limits of their design, we need to extend the accuracy of these models to account for more geometric nonlinearities. This brings us to the last part of this talk, where I discuss how we can extend the original SSMR framework to handle more interesting tasks where we have significant motions in 3D. Now, previously, our models relied on the assumption that the input was sufficiently small to ensure that the control trajectories were near the manifold at the origin. Here, we remove that assumption by approximating the SSM attached to control trajectories. And this approximation will come from essentially a spatial interpolation of local SSM models, and will show that these models are accurate when the control trajectory is sufficiently slow. Furthermore, we show that the model performance degrades gracefully with the speed of this control trajectory. So let me try to make this a bit precise. Suppose I have this continuous reference trajectory that I want my robot to follow. I'll then take discrete points of this trajectory, assume I can find some control to get to that point, and then construct a local frozen in time surface, or SSM, that's anchored to this new forced equilibrium. If I do this for each and every point along my reference trajectory, and then turn the time on, i.e., make epsilon greater than 0, then one can show that a time-varying SSM actually survives as a perturbation of the local SSMs that we've constructed along this trajectory. And that's what we mean by this SSM being anchored to this, this target trajectory. So, this theory is really constructive, because this means that there is hope in learning the time-varying SSM by simply interpolating local SSMs along the control trajectory of the robot. And so that's exactly what we'll do. We'll sample a grid of controlled fixed points in the robot's configuration space, and then construct local models at each controlled point. And in practice, we'll follow the same exact procedure as in SSMR, but now we'll just collect decaying data at each forced equilibrium point. In addition, we'll collect, again, a control trajectory data set in the same way we did in SSMR to calibrate these local models for control. Now, with these discrete models in hand, during the control online phase, what we'll do is we'll interpolate both the reduced dynamics and the decoder maps along this controlled trajectory. And what this gives us is a global model that comes by way of spatial interpolation of these local models, which should give us a more accurate model for control, especially in more nonlinear regimes. This model will be, a good approximation if the trajectory is sufficiently slow. Now, to sort of verify this again and to understand the effect of the control trajectory speed on the accuracy of these models, we'll evaluate the prediction capability of our model as we did in part 1. And what we find lines up with what the theory tells us to expect, which is that the model's performance degrades with increasing speed of the trajectory. And what you see here is, while the original framework that we propose, SSMR, model performance degrades significantly with the speed, we find that the adiabatic SSM models actually degrade gracefully, highlighting its superior robustness on top of these methods. And this figure also highlights that our slow trajectory assumption is actually typically satisfied in practice. Now, what we'll do is we'll evaluate the closed loop performance of our adiabatic SSM model at varying levels of approximation. The 0th order approximation is our SSMR model described in part 1. The 1st order approximation is a model that takes the SSMR model and translates it along the trajectory. And then lastly, the higher order approximation not only translates the manifold, but also deforms its surface along this trajectory. And we expect that, for challenging trajectories, the accuracy will improve with higher fidelity approximations. And that's exactly what we see here when the robot is forced into an S shape to track this sort of 3D trajectory. ASSM outperforms its first order approximation, which in turn outperforms SSMR. We expect this because SSMR should only be, again, accurate for trajectories near the robot's equilibrium point. Now, because the first order approximation model simply translates the SSMR along the trajectory, it doesn't actually capture the higher order nonlinearities that are inherent in this trajectory. And so by allowing the geometry to also vary, adiabatic SSM is able to capture these effects. Furthermore, all of the learned local models are below 5 millimeters in the z direction. And so what we see here is that ASSM can actually track trajectories that are at least a factor of 5 greater in height, which highlights that these ASSM models have an exceptional ability to generalize. Here I show that we can also track arbitrary trajectories, and that we're not necessarily restricted to these periodic regular trajectories. And so in summary, in this part of the talk, what I proposed was a new method that extends the accuracy of the SSM models. And taken all together, I hope that I've convinced you that leveraging dynamics-based priors help us learn compact, faithful, and robust models for continuum robot control. I think this work is really just the first steps towards applying this dynamics-based framework to continuum robots. And there are many fruitful directions for future research. For example, we're currently applying our approach to a real-world trunk robot and aiming to even further reduce the data curation efforts to characterize these systems. Now, one way to do this would be perhaps to learn the model components, the encoder, the decoder, and the reduced dynamics simultaneously using arbitrary data. Currently, we're learning them separately. Now, I would say that doing this in a way that preserves, dynamical structure is an exciting and important next step if we really want to scale these methods. I think another promising direction is to apply these methods to untethered soft robots for navigation and interaction. Extending control-based SSM models with contact could lead to continuum robots that can, interrogate hard-to-reach and safety-critical places. Enabling tasks like, engine inspection and repair, where the soft body of the robot allows it to conform to the tight spaces in an engine without damaging critical components. I think, if we apply these methods to this application, there's interesting questions that follow regarding, what's the appropriate sensor modality to estimate the robot's proprioception, so on and so forth. And maybe these dynamics sort of informed constraints to preserve SSM structure could be used in a co-design framework to help design embodiment and task-based sensor arrangements for these robots to do these interesting tasks. And last but not least, the methods explored in this thesis are general and extend beyond continuum robots. For example, they could be applied to analyze and design, these up-and-coming large sequence models, allowing us to reduce parameters by identifying sort of the dominant parameters in these architectures, or creating architectures that are more robust to noise for time series prediction. This could enable new energy-efficient model architectures that we could then deploy on embedded computers on the edge. And so with that, I'll conclude my talk. But before I take any questions, I'd like to acknowledge the important people who have been a part of this PhD journey. First and foremost, I'd like to thank my committee. Thank you so much for taking the time to be here. I know that this has been a very long day for many of you, and that we had to sort of flex the schedule to make this happen. Mac, thanks for not only serving on one, but two of my committees. You were on my qualifying exam committee, and I appreciate you again taking the time to serve a critical role on this thesis committee. Tawan, thank you for not only serving on this committee, but also for being an amazing department chair. I have a deep respect for all of the work you've done for the department, especially the support that you've given towards this collaboration with the Air Force. And I'm deeply thankful for your leadership. Allison, thank you so much for stepping in at the last moment to chair this committee. Every time I see the work coming out of your group, I'm super inspired by the potential impact of this research direction. And so I can't think of anyone more suited to really chair this defense. So thank you. To Joelle, thank you so much for stepping in at the last minute to serve on this committee. It's been an especially long day for you. I believe it's midnight over there, your time. So thank you so much. I hope Marco will make it up to you one of these days. And then last but not least, I want to thank my advisor, Marco. Marco has, in every sense, been the perfect advisor. He's hands-off, but also a great motivator. I'm continually impressed by his ability to motivate me into doing things that seem impossible. I can't tell you how many times I've walked out of a meeting thinking, that deadline that Marco gave me is impossible, but then somehow still make it while preserving the quality of the work. In all seriousness, Marco, I can't thank you enough for not only allowing me to pursue my interests, but also giving me the resources and the means to do so. Thank you for believing in me, and I look forward to continuing our work together. By the way, here's a picture of Marco exercising his citizenship at the Pentagon 2 months ago. I caught him, practicing his speech for when he becomes the next American ambassador to Italy. And you can count on my support, Marco.
Well, you were not allowed to share it.
Well, I had to. I got clearance to do so. Now, this PhD has been a journey of, exponential learning and growth for me. I just had really an amazing time. And despite the late nights, fighting to meet last minute deadlines, it was just really a lot of fun. And I attribute that to all of my amazing collaborators who helped shape not only how I do research, but how I think about really hard problems. Through our interactions and their mentorship, I've learned how to think with clarity, rigor, and purpose. And that's something that I'll carry with me for the rest of my life. Part of the reason why I've had so much fun is because I get to work with these, really talented and inspiring people. So, first I'd like to thank Professor George Haller for essentially serving as my second advisor. He exercised tremendous patience in allowing me to try to internalize the theory that he's developed. And I can't thank him enough for not only being generous with his time in terms of mentoring me, but also for taking me in as one of his own. I also want to thank Mattia, who was essentially my third advisor, and who played a critical role in the first part of this PhD thesis. I appreciate the long technical discussions we had and the many beers that followed. A special thanks to Ed, who stepped in into the advisor role when Marco was at NVIDIA. The amount of energy and intellect he contributed to our conversations were just truly extraordinary. I admit it was hard to keep up at times, but when I did, it really helped to unbottleneck my research. I also want to thank Florian, the first master student I advised, who brought the idea of SSMs to Stanford and essentially made my PhD. To be honest, I'm not exactly sure who advised who. And I'm tremendously lucky to have spent, late nights in the lab debugging code and writing down formulas with him. I also want to thank Roshan, who's been an amazing collaborator and has played a critical role in the third part of this thesis. He had big shoes to fill when Mattia left, and he not only filled them, but outgrew them. I appreciate the weekly discussions and we have and the amazing ideas that you bring to the table. I want to thank Luis, who's not only been a phenomenal collaborator, but also a great friend throughout this PhD. He played a critical role in the second part of this talk. And, I appreciate the many whiteboard sessions that we had together, and I hope we continue to have many more. To Jonas and Johannes, thank you both for being fantastic collaborators. Jonas brought this adiabatic SSM work to life, while Johannes was really instrumental in developing the robust MPC framework I presented in the second part, and I appreciate you both. Lastly, I want to thank Hugo and Mark for bringing the trunk robot to life. This was really a crazy idea that started 2 years ago, and I'm really impressed with how well they executed this project. I'm lucky to have worked with them. Next, I want to thank my mentors who played an outsized role in shaping my PhD journey and beyond. First, I'd like to thank Ali for not only being a close mentor, but also a friend. I'm deeply appreciative of you sharing your wisdom, energy, and network with me, and I wouldn't trade anything for the many conversations and coffee chats that we've had over the past 2 years. Second, I want to give a special thanks to Anne. She's been there from the start of my academic journey as my department head at the academy almost 14 years ago. She's done so much for me, and it would take another hour for me to really thank her appropriately. So I'll just be brief by saying that, Anne, I appreciate everything you've done for me in this journey. Third, I want to thank Charbel for his support on our various projects, and frankly, for just believing in me. Your dedication to the AI Studio efforts is inspiring, and I appreciate him being patient with me. Last but not least, I want to thank Jason. Even though Jason came a bit later into my PhD, he played an outsized role in shaping it. He's one of the most interesting and thoughtful intellectuals that have come across, despite having a background in policy. We'll just forgive him and forget that. When people talk about Jason, they always say that they're lucky to have had them on their side. Well, having worked with him for the past year and a half, I can see why. I'm glad that you're on my side. So thank you for being an amazing mentor and leader. I also want to give a special thanks to everyone in the ASL. The quality of the people in this group is not only technically, but personally is really second to none. And I'm inspired by each and every one of you every day. To the AI Studio team, it's hard to put into words how lucky I am to be able to work with you all. The fact that we were able to take an ambitious idea and make it a reality is something I couldn't have dreamed of in a million years. And it was all thanks to the collective efforts of this amazing team in making that happen. And there's just not enough time to really thank all of the people who have shaped this journey, but you know who you are. I will take this time, though, to thank my parents who drove up all the way from LA to be here during this special day. Everything that I've accomplished up until this point, I credit to them. Their love and support is what got me this far, and their unwavering belief in me has been a source of great strength and motivation. Okay, last but not least, every piece of work that I've accomplished in this PhD bears the unseen sort of imprint of my wife, Elizabeth. In every moment, I wrestled with late nights, paper and project deadlines. She was there, steadfast, supportive, and selfless. And even though I was, the primary author on all of these papers, she is in every sense a silent co-author. The long hours and relentless demands of this journey were not mine alone. She bore them with me and often for me. And this PhD is as much your achievement as it is mine. I'll forever be grateful for the love, patience, and sacrifice you've given throughout this journey. To my daughter, Estelle, thank you for letting Daddy miss out on some of our play dates to go and chase, his dreams. I hope one day you'll have the opportunity to chase your own, and I'll be there every step of the way. And so with that, I'll conclude my talk. I'm happy to take questions. Thanks for being here.
Hey John, I have a question. I'm not sure if someone else
Okay.
in the room is talking. I can't really hear.
No, no worries. Yeah, go for it.
Okay, yeah. So my question, actually, if you could maybe go back to the beginning of your presentation, the first part, you were comparing some of the different models and their different performance,
Sure.
and I noticed you had put the dimensionality of the models, and I think the ones you were looking at were 5-dimensional or 6-dimensional.
Hmm.
And so I'm assuming that's just coming from the SVD, like you're just choosing 5 or 6 dimensions to capture, the 99% of the singular value, like energy or whatever.
That's right. Yeah.
Um, so maybe could you just comment on like how much better the models get if you do include any more of the modes?
Yeah.
Because it was actually quite a bit smaller dimension than the other models you were comparing against. So like not only were you getting like better performance, but it was with a lower dimensional model.
Yeah.
Um,
Yeah, that's a great question. So I'll just repeat it here. The question was, if I increase the dimensionality of my model, do I expect better performance? In theory, you should expect better performance. The challenge is that when you're doing this SVD, you might actually pick up numerically like just noise. And so if you try to increase the dimensionality of the model, it actually becomes more parametrized. You become more sensitive to the noise. And so what we found is actually that if we sort of, if we can actually reduce the number of dimensions by taking into account symmetries, the models actually perform more robustly, which is counterintuitive. But the idea is really that, we're trying to learn these, very robust structures. And so we shouldn't have to rely on sort of more modes, if you will. We should really just focus on the ones that really matter. Otherwise, we run into the issue of overfitting and not generalizing.
Okay. And then as like a follow-up question, like is there anything about the particular form of your model that makes the actual control like algorithm implementation harder? Or
No,
like,
no,
okay.
no, no, actually it's the same SCP that we use. We're using Gusto as well. There's nothing that changes. Um,
Okay,
yeah,
cool. Thank you. Nice
thanks.
presentation.
Thanks, Joe. A miss. Go ahead. Yeah.
Are you in your framework, are you allowed to apply control that could potentially destabilize the
Mm.
more informative data, or are you constrained to only identification with stable data?
Yeah, in this case, that's a really good question. In this framework, we assumed that the fixed point that we're attaching this SSM to is stable. There is, a deeper theory that guarantees that these things persist for unstable systems, even systems that have mixed mode stability. Um, the practical challenge is like collecting the data to characterize this. Um, and so, we didn't consider the case where we have a stable system, we introduce control and then it becomes unstable. That would be interesting future work though, because indeed this is the case for a lot of physical systems.
Yeah, with online for
Yep, Shreyas, go ahead.
Hey, first of all, awesome talk. I want to use your slides as an example for my students here.
Thanks.
Beautiful, beautiful stuff. Um, I was curious actually on this slide, kind of following up on Joe's question.
Sure.
So the Koopman and BMD methods, they require you to pick some observable space as well, right?
Right.
Could you talk a little bit about like I don't know if you actually explored in your comparisons
Mhm.
how those observables matter, or if, and ideally, maybe there's some way to show, like, if you pick the right observables, maybe they're even like somewhat equivalent to a spectral subspace. But I don't really genuinely know. I'm curious.
Yeah, that's a great question. The question is, for these extended dynamic mode decomposition sort of models, you have to pick like a dictionary to characterize your observables, and the theory is that if you increase the number of features that you work with, it converges to a linear system that is globally linear. The challenge is that these things are infinite dimensional. And so, you're sort of bottlenecked by that. The hope is, though, that when you do pick these features, that you will sort of have a good enough representation. Now, to answer your question, Shreyas, the features that we work with were the monomial basis. So we didn't explore any other features. This was pretty standard, I think, in the continuum robot literature. I think because I'm not sure if the other features just didn't work, but monomial basis was the standard. Now, the challenge was that if we increase the number of dimensions, especially for extended dynamic mode decomposition, we actually found that we would be really sensitive to noise in the data. So we would essentially overfit.
That makes sense.
And we found that this 120 dimensional model was actually a nice sweet spot where it worked decently, but it essentially, as you increase, it just overfit more and more, and the performance just degraded.
Cool. Thanks. Great work, John.
Thanks, Rez. Yeah, that's a really good question. I would say that one of the assumptions that we made here was that our model is like perfectly characterized the SSM. And then we would sort of roll in the model sort of error or the approximation of this SSM in the disturbance term, right? It would be really interesting to go and try to characterize or have like an additional term that takes into account the fact that we've learned this SSM imperfectly. And in that case, you might have to leverage some statistical tools to come up with a bound for this. But we initially tried this. It was really difficult to come up with a practical bound. Everything was just super loose. But it would be an interesting thing to do. But we didn't consider that here.